Let's start with exercise number 9. Exercise number 9. At a moment in time, t0 is equal to 0, a force that depends on time according to the law F is equal to eta t, where eta is a defined constant, begins to act on a small body of mass m, that is lying on a smooth horizontal surface. The angle between this force and the horizontal plane is alpha. Find a velocity of the body at the moment in time when it comes off the surface, and B, the path that body traverses until this moment in time. So I'll draw a picture. So we have a smooth plane, and a body on it. Maybe here is mass m. This is dash line. Force. Force F. Force F, and angle between the force and the surface is equal to alpha. And we have to find the velocity at a moment in time when body comes off the surface, and the path that the body traverses until this moment in time. Okay, maybe you have any ideas. Maybe you have some ideas for this exercise. Okay, let's find the condition of taking off, the condition of breaking contact between body and the surface. What is this condition? Okay, maybe it will be useful to draw some forces that act on our body, on this body. Let's draw some forces. Okay. Yes. I see. Okay. This is good. mg is a gravity force. Gravity force. This is correct. This is correct. But this force, we don't need it. We don't need it because we already have F. We already have F force here. We already have F. One more force. We have force of normal reaction. Elastic force that acts from surface on body. Normal reaction. Normal reaction. And when the body takes off, normal reaction will be equal to 0. Will be equal to 0. And the condition of taking off is when vertical part of force F is equal or more than gravity force. So I have to represent force F. I have to represent force F. Maybe I'll draw this in this way. I have to represent force F as like sum of two parts. Now I'll draw this. We can always do that. We can always do that. We can always represent a vector as with combination of some another vectors. So this is vector F. This angle is equal to alpha, and here we can represent force F with sum of two forces. This is horizontal part, horizontal H, horizontal part, and vertical part of this force. Horizontal and vertical part. Is it clear?
Yeah.
Okay. So you can remember parallelogram law for sum of vectors. For sum of vectors, and we have used this law here. Okay. How to find modulus of modulus of vertical part, a vertical part and horizontal part, because here the angle that is 90 degrees. 90 degrees. So we have the triangle. We have triangle with angle that has 90 degrees. Okay, what can you say about FV and FH? And now we are studying modulus, so we don't need vector. We don't need vector. We don't need vector above f. So you have written correct formula, but we don't need this sign above f. Yes, okay, that's correct. That's correct. That's correct. I agree.
Teacher,
Yes.
because of this line, these two angle is the same.
This angle is the same.
Oh, sorry. So,
And if
okay, and no.
yes, okay, good. Good. This is correct. This is correct. This is correct. And the condition of taking off is FV is equal to mg. Is equal to mg. This is condition. So we can make substitution. F sin alpha. F sin alpha is equal to mg. Is equal to mg, and one more we can make another substitution. Eta t maybe I'll write lower index c. It makes condition. Okay, let's make it c. C. Time of taking off, or time of Okay, let's write this as C. NTC sin alpha is equal to mg is equal to mg is equal to mg, and we have time of slicing, or time of motion on the surface. It is equal to mg divided by eta sin alpha. Okay, is it clear for the moment?
Yes.
Yes, okay, that's great. And when we have time, can we find velocity? Can we find velocity at the end of the motion along the surface? Maybe we can. Because we have horizontal part. We have horizontal part of the force. We have horizontal part, so I think we can try to find. We can try to find this. We can try to find this velocity. Velocity of the body at the moment in time when it comes off the surface. Maybe let's remember the second Newton's law. Let's remember this. The second Newton's law. According to this law, m first derivative of velocity now I am considering the projection of vectors on the direction of motion. So I don't need to use vectors. I am using scalars. And this is equal to projection on horizontal direction. So it is equal to horizontal path, because the body moves in horizontal direction when it moves along the surface. And it is equal to F cos alpha, and it is equal to eta t cos alpha. And what do we have? We have we have m dv by dt, and it is equal to eta t cos alpha. Okay, so we have obtained ordinary differential equation. And if we solve this, we will obtain velocity as a function of time. And how can we do this? How can we solve this ordinary differential equation? So, don't have any ideas. Okay, maybe I will clean some space on the screen. I will clean some space because I need this. But it is necessary not to clean. It is necessary not to clean something that is something that we need for the moment. Okay, I'll clean this and okay, how to solve this ordinary differential equation? It is a simple case. It is a differential equation with separable variables. This is a differential equation with separable variables. What does it mean? It means that variables may be separated. To separate variables, we have to do some algebraic actions. To make v on one part of equation and t in another part of this equation. So let's try to do this. And one more. Differentials when variables are separated, differentials mustn't be in denominator. So now here variables are not separated because we have both v and t in left side, in left part, and we have differential in denominator. So what do we need to do? First of all, we need to get dt from here. So we have to move this to this part. Okay, how will we do this? Any ideas? Or not?
Okay, I can.
Okay. Okay, maybe. Oh, yes. Okay, when we work with equations, it is always possible. It is always possible to do the same action with left and right sides of this equation. It is always possible. And what do we need to remember is that we always have to do the same action with left and right parts. So now we have to move this from left side to right side. We have to move this differential dt from left side to right. Okay, let's do the same action with both sides. We don't have many actions to do. We can add something, we can subtract something, we can multiple, or we can divide, or we can take square root, for example. So let's do this. M dv by dt multiplied by dt, and we have to do the same action with the right part of equation. Это t cos alpha dt. Okay, is it clear for the moment?
Yeah.
Okay. Okay, so we can simplify the left side. We can simplify, and we have m dv. M dv is equal to eta t cos alpha dt. And now the variables are separated. The variables are separated because in left part we have only v, and in the right part we have only t, and there are no differentials in denominators. So variables are separated, and when they are separated, we can integrate this differential equation. We can take integrals. M dv is equal to the integral of eta t cos alpha dt. Okay, and now the next step is to write is to write integral limits. Integral limits. The lower integral limit we can get from the initial condition. From the initial condition. From the initial condition. So here will be initial time, and here will be initial velocity. Initial velocity. Okay, according to the description of the exercise from PDF file that I have sent to you, what initial time we can write in lower integral limit. In lower integral limit, yes, this I agree. Okay. Okay. Okay, that's correct. That's correct. And what about initial velocity? Yes, yes, that's correct. Because according to the description, we have an information that force begins to act on a small body of mass m that is lying on a smooth horizontal surface. So at the initial moment of time, the body was lying. It was lying, and it means that it had the velocity that was equal to 0. Oh, of course, the velocity is definitely was equal to 0. And the upper integral limit, we have to write here some moment of time and some value of velocity. And what do we need more? We have to reassign. Variables in integral. Because in mathematics it is not allowed to use the same letters here and here. It is not allowed to use the same signations, the same letters. Letters must be different. Here and here. And in order to avoid the same signations, I put this head above V. Okay, so can we calculate these defined integrals? Okay, left side is good. Yes. Okay. Okay, and it is necessary to divide this by 2. It is necessary to divide this by 2. Because according to the table of integrals, x in nth exponent is equal to x n plus 1 divided by n plus 1 and plus constant. So because of this we have 2 in denominator. Okay, this is correct. This is correct, and according to this, we have v. We have v is equal to eta t squared cos alpha divided by 2m. Do you have any questions about this? Do you have any questions?
No.
No. No. Okay. The next step is to make substitution. To make substitution, we want to find the velocity at the end of the movement along the surface. At the end of the movement along the surface, or at the end of the slicing along the surface. So it is necessary to substitute this time here. So we have eta cos alpha, eta cos alpha divided by 2m multiplied by m squared g in second order eta and sin squared alpha squared alpha. And after making some algebraic transformations, we will have m g in second order cos alpha divided by 2 eta 2 eta sin second order alpha. Sin second order alpha. Okay, do you have any questions?
No.
No. Okay, this is the answer for the first part of the exercise. This is the answer for the first part. Answer for the first part. Okay, let's try to solve the second part. The second part is the path that body traverses until this moment in time. I'll clean some space on the screen. I'll clean some space and this is necessary. This is necessary. And this is the answer for the first part. And how to find path? How to find path of the body? Okay, maybe, but the first that this should be written here. Oh, should be written here. And moreover, we don't need to use the second order differential equation because we have already had velocity. We have already got velocity, so we can use the definition of modulus of velocity. Can you remember that this definition? And what do we have when velocity is not constant? This formula can be used only in the case when v is equal to const. But we don't have this case. We don't have this case because velocity depends on time. Velocity depends on time. So we have to modify this formula. We have to modify this. This is radius vector. Yes. Okay. Actually, we have two definitions of velocity. We have two definitions. The definition of vector of velocity vector of velocity is equal to first derivative of dr by dt, and modulus. Oh yes, I see. Modulus of velocity can be written as first derivative of path by time. And now we need to use this. We need to use this definition. So let's do this. Let's do this. Let's do this. Let's do this. And let's make substitution. Let's make substitution. D S by dt is equal to eta t in second order cos alpha divided by 2m. Okay, so now we have first order ordinary differential equation, and it is necessary to solve this. How will we do? Okay, this good idea. Okay, good idea. ds is equal to t in the second exponent. I'll yes, second exponent. Okay, and what about integral limits? What about integral limits? Yes, 0 and s. Oh yes, good. Okay, that's correct. That's correct. That's correct. That's correct. Let's calculate these integrals. Okay, maybe it is necessary to clean some space. I will do this. Maybe let's clean some space. Let's clean some space. Okay, here. Yes, that's correct. Okay, maybe it is difficult. It is difficult to use mouse to to draw on the screen. Yes. You have forgotten about 3 in the denominator. So here it is necessary to draw 6 because we have 2 here and 3 here. After multiplying, it will result 6. Sorry, we have it here. Sorry, so yes. Okay, so we have obtained 6 eta square sin. Yes, this is correct. This is correct answer. Maybe I'll make lower index C. This is answer. This is answer. I agree. I agree. So C is equal to M in second order, G in third order, cos alpha divided by 6 eta second order and the sin in third order alpha. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, and now I am wondering what to do. What to do the next, because we don't have much time. We don't have much time. Maybe let's try to solve number 17. Let's try to solve number 17. I hope we will solve this before the end of the lesson, because we don't have much time. Don't have much time because these exercises are difficult to understand, and moreover we have to study them in English. We have to learn them in English, and it is not my native language, and as I understand, English is not your native language, so it is difficult for us to study physics. Okay, number 17. Number 17. Number 17. A thin homogeneous copper rod of length L, and mass M, uniformly rotates with the angular velocity omega in a horizontal plane around a vertical axis that passes through one of its ends. Find the tension force in the rod depending on the distance r, to axis of rotation, and the rod extension, okay, maybe I'll draw a picture. I'll draw a picture. This is the axis of rotation. Here we have a vector of angular velocity. And here we have this rod. And how to find tension force depending of the distance r to axis of rotation. The length of the rod is equal to L. And distance to axis of rotation is here. So what is the main idea? Let's have a look at a small, infinitely small part of the rod. It is here. infinitely small part, like this. Infinitely small part. Infinitely small part. It has size. It has size dr. It has size dr. Infinitely small part of the road. And what is the velocity of this small part? Velocity of this part dr is equal to v. V is equal to omega r. This is the velocity of this small part of the road. And what is normal acceleration? Normal acceleration of this infinitely small part is equal to omega in second order multiplied by r. Multiplied by r. Multiplied by r. And according to the second Newton's law, we have mass dm. This infinitely small part of the road has mass dm. Mass that is equal to dm. Mass that is equal to dm. And according to the second Newton's law, dm multiplied by acceleration, normal acceleration, is equal to some part of force that acts on this part of the road. So let's find differential of mass. Let's find this differential. Let's find this differential. Let's find this differential of this mass. Dm is equal to density multiplied by volume of this infinitely small part of the road. And this volume is equal to rho is equal to rho multiplied by square of cross section of the road, multiplied by its length dr. Okay, and what about density of the road? It is said that the road is homogeneous. And it means that it means that we can write that rho density of the rod is equal to mass divided by its volume, because the rod is homogeneous according to the description of the exercise. According to the description.
Teacher.
Yes.
Teacher, this symbol is G.
No, it is not G, it is Greek letter rho.
Rho.
Rho, Greek letter.
Oh, okay.
It means density. Density. Because G is acceleration of free fall. Acceleration of free falling body. So rho is density. And density is equal to mass divided by volume. And this is equal to mass divided by square of cross section multiplied by the length of the rod. And M L D R. M L and D R. DR. Okay, and let's make substitutions. Make substitutions. dm we put here, and an normal acceleration we put here. And as a result, we have obtained m omega in second order divided by L divided by L R and D R, and it is equal to it is equal to df. It is equal to df. Okay, variables are separated. Variables are separated, and it means that we can integrate. We can integrate this equation. We can integrate this equation m omega in second order divided by L R D R and the D R. Okay, and what about integral limits? What about integral limits? What about integral limits? We have here we have force. Here we have force from 0 to F. No, from 0 to F. And what do we have? What do we have in the right part? This part of the road. This part of the road acts on infinitely small part dm. So this part acts on dm. This part acts on dm. So we have to put we have to write lower limit r and upper limit L. So from for this part of the road, we have limits from R to L. Okay, is it clear or not?
Yes, it's
Good. Good. So let's calculate. Let's calculate this f. F is equal to m omega divided by L. L in second order divided by 2 minus R in second order divided by 2. And we have m omega in second exponent L 2L L squared minus R squared. Okay, this is the this is the answer. This is the answer for the first part of the exercise. This is the answer for the first part of exercise. Answer for the first part of the exercise. Okay, and what about the second part? The second part, and road extension. Road extension. Road extension. So let's clean some space. Let's clean some space for this. Let's clean some space. Now we have force. We have force that acts on small part dm. Force that is impressed on dm. That is impressed on dm, and we can use this. We can use this, and we can use Hooke's law. We can use Hooke's law. According to this law, we have tensile strength. Tensile strength that is equal to Young's modulus multiplied by epsilon, multiplied by epsilon. And let's use this Hooke's law for this part, for this small part of the rod. For this small part of the rod. We know that we know that tensile strength is equal to tension force, or force of tension, tension force divided by square of cross section. Square of cross section, or area of cross section. So F divided by S divided by S divided by S, and according to this we can write this that S is equal to M divided by rho L. We can find we know, according to the description, we know that rod is made, the rod is Cooper, rod is Cooper, and it means that we can find its density and its Young's modulus, because this value is known. This value is well known. We can find this from the internet, so we can write this rho L F divided by M and if we substitute this here, we will obtain L and M, so rho omega in second order divided by 2 L and M simplified, L in second order minus R in second order, minus R in second, minus R in second order, Okay, and what about elongation? What about elongation of small part of the rod dm? Elongation is equal to delta R divided by dr, as you can remember from our lectures, there was a formula that relative elongation is equal to absolute elongation divided by initial length of the body, and we have used this formula here. We have used this here. Okay, let's make substitutions. It will be here, and this will be here.
Yeah. Okay. Can I ask some question?
Yes.
Here, this to this, is rho L M omega divided by 2 rho and rho. Yes. Yes.
No.
Yes.
No.
No.
No. No. It is. This is rho. This is
Rho
L.
L.
F.
What F is
Force.
this multiply. Yes, it's correct, teacher. Here is L. This part is L. This is L, right?
Yes.
This is okay. Okay, thank you, teacher.
Okay. Okay. So we have obtained differential equation. We have obtained differential equation d delta r divided by dr, and it is equal to E Young's modulus rho squared omega divided by 2 L squared R squared. L squared and R squared. Okay, so let's separate variables. D delta R is equal to E rho omega in second order divided by 2 L in second order minus R in second order multiplied by dr. Multiplied by dr. Multiplied by dr. Yes, I have to optimize space on the screen. I have to optimize some space, and yes, we will have here here we have integral d delta r is equal to integral E rho omega squared divided by 2 L minus R minus R squared dr. And we have to find rod extension. So here we will put integral limits. So we have to consider all the rod. So here we have to put 0. We have to put 0. And here we have to put 0. We have to put 0. And maybe here we have to put L, and here we will put maximal elongation, maximal extension. And as a result, we will have delta L is equal to E rho omega in second order divided by 2 L squared multiplied by R minus R in third order from 0 to L, and this is equal to E rho omega squared divided by 2 L in the third order minus L in third order divided by 3 divided by 3, and as a result we will obtain E rho omega squared E rho omega squared divided or maybe I have I have made a mistake. I have made a mistake because E is here. E was here, not in the right part. So as a result, we will have. I have made a mistake. Double E. O. E. Young's modulus is here. Young's modulus is here. So yeah, this is correct. So divided by 3 E and L in third order. Yes, this is the answer. This is the answer. Okay. It is R.
R. Oh.
Okay, do you have any questions? Okay, so the next homework will be number 10. Number 10. Number 10. And I have to remind that these homeworks are necessary. They have to be done. they have to be done, and the previous homework, only one student has sent to me. Previous homework was sent by only one student. So other students have to have to do this too. Okay. Because I need something to to evaluate your knowledge at the end of the semester. So let's do these homeworks. Okay, do you have any questions? No questions. Okay,